Okay, today we're going to talk about pH and acid concentration, and we are going to start with the equation that we've been working on, that we've written like 3 or 4 times now, and it's the water dissociation equation. So H2O, got 2 of them. That makes, and you guys remember what the products are?
H3O, or hydrogen ion plus.
All right. So we've got H2O plus H2O. We're going to make, what was that again?
Hydronium and hydroxide.
Hydronium plus hydroxide. And what we figured out last time was that this is a that for every, well, first of all, it's an equilibrium. And whenever we have an equilibrium, that we're going to have a equilibrium constant, that we can take our concentrations and put them into this construct where we have an equilibrium constant. And this one is going to be specific for water. In fact, it is called Kw, and this is the water dissociation constant. All right, and this Kw, okay, we set it up just the way we've done all the other ones. And whenever we have concentration of stuff, we put the products on the top. Okay, and on the bottom we put the reactants, but both of our reactants here are water, and you can't really have a concentration of water in water. All right, water is a pure, in this case, is considered a pure liquid, and so we don't include that into our equilibrium expression. So we're just left with these two. Okay, and this actually has a value. This equals 1 times 10 to the negative 14. That is the value of this expression. This is the water dissociation constant, 1 times 10 to the negative 14. Well, but from this, though, we can figure out what the concentration actually is of hydronium and hydroxide. Because from this, if for every hydronium we make, we also make another hydroxide, then for every one of these, we make one of those, which means that these two have to be equal to each other, right? So let's assign a value. And we'll call them x, because we want to figure out how much it's going to be. So this winds up being x squared equals 1 times 10 to the negative 14th. Now, if we're really going to be algebraic, we would move this to the other side, and x squared minus 1 times 10 to the 14th, and then we factor it, and we get 2 solutions, and that's how you get a positive and negative solution. We can just square root it. Square root both sides, and this is going to be x equals, what's the square root of this going to be? You guys should be able to figure this out just by looking at it. The square root of 1 times 10 to the negative 14, okay, would be the same thing as this exponent divided by 2, because when you take the square root, the way you do an exponent square root is you divide by 2. And this would be 1 times 10 to the negative 7th. This equals the concentration of hydronium and the concentration of hydroxide. They're both the same. Okay, so let's think about the implications here. Water does dissociate on its own, but it does it so rarely that at any particular time there's only 1 times 10 to the 7th moles for every liter of water that is actually dissociated. But when it dissociates equally into acid and base. And so by definition, water is neutral because it has equal parts acid and base. And that's the concentration of the acid and the concentration of the base that it has in the water. Yeah? Okay. From this, we establish a new way of describing how acidic something is. And we call it pH. All right? pH is equal to the negative exponent of 10 of the acid concentration. So the negative exponent of 10. Well, here's our neutral, right? Our 10 to the negative 7th. So the negative exponent of 10 would be negative of the negative 7. Yeah? So it would just be 7. Does that make sense? Okay, so the pH of a neutral solution then is going to be 7. Okay, so neutral solutions have a pH of 7. But there's actually a formula for this, and there's a math formula for you people that are more comfortable using the math formulas. And what pH is equal to negative log of the hydronium. This log function is this. When you find the log of something, you're actually finding the exponent of 10 that will equal that number. Okay, and there's some, it's you know, if you have a fractional log, if it comes out as a decimal, then that means there's some fractional exponent, your combination of positive exponents and fractional exponents to give you your value. That's how it comes out. Okay, and then the negative just makes that value a positive number. So instead of dealing with a negative 7 pH, it's a positive 7 pH. That's all this negative does. All right, so if we have a hydronium concentration of, say, 1 times 10 to the negative 3rd molar, how does this compare to something that's 1 times 10 to the negative 7th molar? How does this value compare with that value? Is this larger or smaller?
It's larger.
This is larger than that one, yes? Okay, so what would the negative exponent of 10 be here? Be positive 3, yeah? All right, so if there's more hydronium, that means this is going to be more acidic than 1 times 10 to the negative 7th water, right? It's going to be more acidic than neutral because there's more acid ion in that solution, yeah? But the pH was going to equal 3, the negative exponent of 10. So what does this tell us about about our trend in pH? That if neutral is 7, then something a pH of 3, is it going to be acidic or alkali? It's going to be acidic. So things with a pH less than 7 then are going to be acidic, and that establishes our scale. Okay, so that 7 is our neutral value, neutral pH. It's the same pH as water. We have less than 7, everything over here is acidic. And everything to the other side, everything to the other side is going to be alkali. So if you have a pH greater than 7, that means that this exponent is now less than negative 7. Less than negative 7, like negative 8, negative 9, negative 10, which means you have much smaller values of hydronium, which means you have greater values of OH. Oh, we need to talk about that. If this right here was our concentration of our hydronium, what would be the concentration of our hydroxide? If our hydroniums tend to the negative 3, then our hydroxide, because remember, they have to multiply to give us 1 times 10 to the 14th. So if we have an acidic solution of 1 times 10 negative 3, our hydroxide concentration is 1 times 10 to the negative 11th. And this is way smaller than this, right? Okay, which low base ion, high acid ion, this is an acidic thing. So if we're on the other side, so if we have a pH of 8 or 9, that means we have our hydroxide concentration is going to be 6 or 5 or greater, -6, -5 or greater. You guys following that? Okay. Now you can do the same thing, and I do this at the risk of confusing you. There is also a thing called POH, which is the same thing except you do it for the hydroxide concentration, and it works exactly the same way. It's just it's the rest of 14. So let's say we have a pH over here of 10. Okay, this would result in a POH equal to 4, and these two are always going to add up to 14. Okay, always. The pH and the POH of a solution will always add up to 14. So here's what I'm going to expect you guys to be able to do. We have one solution with a hydronium ion concentration of 1 times 10 to the 5th molar.
The piece for power.
Power? You really? Seriously?
Yeah.
You just looked it up? Mm-hmm. Right on. There you go. P stands for power. Because it would be the power of the... Yeah, that makes sense. Okay, so we have a hydronium concentration of 1 times 10 to the negative 5th. We have another solution with a hydronium concentration of 1 times 10 to the negative 6th molar. And we have another one with hydronium concentration of 3 times 10 to the negative 6th molar. What would the pH of this be?
That would be 9.
Nope. No, the pH of this.
Oh, sorry.
Don't overthink it. What's the exponent?
It should be 5.
Just be 5. Okay, pH of this one would be 6. Here's my question. Here's the third solution. Is this going to have a pH? Is it going to be less than 5? Between 5 and 6? Or greater than 6? This number here is going to have a pH. Where is it going to fit in there? Uh-huh. Okay. Is he? What's that? Would it equal 6? Not quite. Okay. The 3 alters the number. Okay, and it is possible. Remember, it's the negative exponent of 10 of the acid concentration. The acid concentration is still 3 times 10 to the negative 6, and there's an exponent that we can raise 10 to that's going to get us on that number. It'll be a fractional exponent, but it'll be there. The question is it in between 5 and 6? Is it less than 5 or greater than 6? You say in between. Why? Okay. Okay. It is in between 5 and 6. And this is a math thing that students tend to struggle with. And so I want to make sure that we're clear on this. 3 times 10 to the 6th, is this greater than or less than 1 times 10 to the negative 5th? How does this compare to that? Okay. This value is less than 1 times 10 to the negative 5th.
Because the exponent value is higher and it's negative. So.
Right. So because 10 to the negative 6th is smaller than 10 to the negative 5th, right? Okay. This fits somewhere in between. So this would actually have a pH of something like 5.8, maybe. Okay, it'll be slightly less than 6. There we go. Okay. And so here's how you figure it out. You go to your calculator. You can actually do this. You'll see this button right here. This log button. Okay, so you would do 3 times 10 to the negative 6. You guys need to know, by now we should know how to put our exponents into our calculators. Okay, and then we hit the log button. And then we hit the negative. And this would actually be, so I guess 5.8 was wrong. 5.52 would actually be this pH. Yeah? Cool on that? Okay. Last thing we need to cover is go back to our Ka for a minute. Okay. Frequently, when we're talking about an acid in general, we can use this A as the conjugate base, and it just means H acid is what it stands for. HA for the acid with the hydrogen on it. That makes sense to you guys? Yeah. It's like X, acid X. We're just calling it A, and A minus is the conjugate base, and HA is the acid. Okay. The Ka from yesterday equaled H3O plus over A minus over HA. And this is if we have a weak acid that will partially that will partially dissociate, doesn't completely dissociate. Ka, though, can vary, and we can have different values of it, where if you have a Ka greater than 1, that means our numerator, okay, numerator values are larger than our denominator values. And so more of our acid has dissolved and has dissociated than not, which means it is a stronger acid. Okay, it's not a strong acid, it's just stronger than acids with a Ka that's less than 1, because it has more of its original form than what it has dissociated. Okay, and you may have to compare Kas and tell me which one is the stronger acid. That's all. Here are these different acids with their Kas. Which one is the stronger acid? You look at the Ka and if it's whichever one has the greater Ka is the stronger acid, because it will dissociate more. I believe that is it for today. So there you go.